Welcome to Let's Get to the Marks, going through the part two of a three-part series on aromatic chemistry for AQA, looking at the Physics and Maths Tutor website, working through their revision pack on aromatics chemistry. It's a little bit of a poo video, this one, because I'm just trying to bang out as many as I can before the exam, so quality down a little, never mind. The reaction between propanol chloride and benzene is an example of acylation. Which is the correct representation of the part of the mechanism of this reaction? Okay, so look at A. First of all, what we have with A, we're looking at the reaction of propanol chloride and benzene and just any part of that mechanism. So what's wrong here? Well, the chlorine normally breaks off during acylation to leave the cation. And here it's showing the chlorine donating a pair of electrons to that single bond. That would become a double bond. That's not possible with chlorine. That's not how it reacts. The arrow should be going the other way from the bond back to the chlorine. So that one's wrong. Now let's check out B. B shows AlCl3 donating a pair of electrons to chlorine. Again, aluminium is not an electron donor. It's only got 3 electrons in the outer shell, if you think back to basic GCSE modelling, so it doesn't have a spare pair of electrons to donate to the chlorine. What normally happens when it forms AlCl4 is the chlorine donates a pair of electrons to the aluminium, which it can accept in its outer shell because it has room. So that's completely wrong too. If we go down to D here, not giving you any hints at the answer, of course, but if we go down to D here, we can see the bond. From the acyl group being donated next to the carbonyl bond, being donated to stabilize the benzene ring. Actually, what happens during substitution onto the benzene ring is that one of the hydrogen atoms attached to a carbon atom on the benzene ring donates its pair of electrons from its bond back to destabilize the broken ring or the horseshoe shell. And there we go. Those 3 answers are all incorrect. And of course, the correct one is C. And what we can see with C, a curly arrow, which represents a pair of electrons being donated to that positive carbon atom on that cation there. And that would make sense. Carbon's only got 3 bonds there. It's willing and able to form another bond. It's ready to accept a pair of electrons, and it gets that from the delocalized ring, which is temporarily broken and then reformed when the hydrogen donates the electrons back. Okay, let's zing on to the next question. So that one's correct. Now we want to bust down and look at question 3. Okay. So for question 3, data about the hydrogenation, fancy word, means adding hydrogen, of cyclohexene and of benzene are given. We can see for cyclohexene, which has 1 double bond, the enthalpy of hydrogenation is minus 120 kilojoules per mole. The minus means it's exothermic. And for benzene, adding 3 hydrogen molecules is minus 208 kilojoules per mole. Now, you might expect it to be minus 360, 3 times more than cyclohexene. Explain the bonding in the shape of the benzene molecule. Compare the stability of benzene with that of the hypothetical cyclohexa 1,3,5 triene molecule. Use the data in your answer. This is a 6-mark question. It's basically broken it down for you, saying you're going to get 2 marks for each section. It's basically mentioned that you need to talk about the bonding in benzene, you need to talk about the shape of benzene, and then you need to talk about the stability of benzene. So that's actually in that stem of the question of A. So why don't you pause the video, have a go, see if you can talk about the bonding for 2 marks, the shape, and the stability. Unpause the video, and then we'll go through the answers. Okay, bonding. Each carbon atom is covalently bonded to 3 other atoms. So think about a benzene ring. It's got a carbon atom either side of it and 1 hydrogen coming off. Obviously, C6H5 is the formula for benzene. So what's unusual about that is that normally carbon, which is in group 4, would have 4 electrons in its outer shell. So it would have 2s2 and 2p2. However, one of those electrons has been stuck into, one of those unpaired electrons has been dumped into the middle of the benzene ring to form the delocalized ring of electrons. And this is where the p orbitals, so the electrons from those 2 p orbitals in each of the 6 carbon atoms, 1 electron from the 2 p orbitals has been shoved in there and has overlapped to form what's called a pi cloud. And so, yeah, that's all you need to discuss on the bonding in order to get the 2 marks. Now, for the next 2 marks out of the 6, what you're going to need to do is talk about the shape, because that's what it basically alluded to in the question, or the stem of the question. So the shape of a benzene molecule is planar, which means the hexagonal ring is all in one plane. So think of a piece of paper just held sideways while you're looking at it. And the carbon atoms, the 2 carbon atoms to the hydrogen in each corner, or the carbons all in the ring, they all have a trigonal planar shape and a bond angle of 120 degrees. The delocalized ring, which is inside that hexagonal ring, is actually spread above and below the ring, a little bit like the buns on a burger. If you imagine the hexagonal ring is the meat in a burger, and then the bun at the bottom and top is the delocalized cloud poking up and down below. And that's formed because of all the overlapping p orbitals. Now, the next mark that we would get, the next 2 marks, is for talking about the stability of a benzene compared to the cyclohexatriene, whatever the numbers were. I can't be bothered to go back up and look, but the cyclohexatriene, it had 3 positions. I don't know, 2, 4, 5, whatever, 2, 3, 5, whatever it was, or 1, 3, 5, whatever it was. So the stability of the cyclohexatriene is shown to be less stable than the benzene ring. And why is that? Well, the enthalpy of hydrogenation of cyclohexatriene is 360, because it's 120 kilojoules per mole exothermic hydrogenation of each double bond, and cyclohexatriene has alternating double and single bonds. However, benzene, you would think, might be similar, but it only has 200 or minus 208 kilojoule per mole. So it's less exothermic, its enthalpy of hydrogenation. And this is because of the increased stability of the benzene ring. We actually say that the minus 152 kilojoules less exothermic that it is known as the energy of stabilization. The bond lengths of the benzene within the carbon atoms all around the benzene are in between the bond length of a single and double bond, whereas in the hexatriene, they actually have double bonds, then single bonds. And of course, double bonds are shorter, single bonds are longer. And this decreases the stability of the hexatriene, the fact that the bond lengths are all different, whereas in a benzene ring, the bond lengths are all the same. It's in between the bond length of a double and a single carbon-carbon bond. Moving on to the final bit, the enthalpy of hydrogenation of cyclohexa 1,3-diene is not exactly double that of cyclohexene, so just the value for the enthalpy of hydrogenation of cyclohexa 1,3-diene and justify your value. So we might think that when you've got one double bond in a cycloalkene, that to add hydrogen across it costs you, or releases, minus 120 kilojoules per mole. If you had 2 double bonds, right, it should be minus 240 kilojoules per mole. But so what they're saying is it isn't minus 240. And you'll get a mark for saying actually it's less than 240. And you need to state somewhere between minus 121 and minus 249, so that you've appreciated that it's more than minus 120, more exothermic than minus 120, but less exothermic than minus 240. So it's a bit more stable because it releases less energy when hydrogenated, which means it's at a more stable position. Now, why is it more stable? The reason why the diene is more stable is to do with the distance between the 2 double bonds. The 2 double bonds are actually only one single bond apart, and this means there's some overlap between the p orbitals in the double bond and some delocalization which stabilizes it. Now, if you look at my incredible drawing in black here, you can see in this diene, the 2 double bonds are more than one single bond apart. This means there's less overlap between the p orbitals, less delocalization, and we would expect that to have an enthalpy of hydrogenation closer to minus 240, if not minus 240, because there's barely any delocalization and the extra stability that that provides. But whenever the single bonds in a diene or a triene are, well, which they would in a triene, but whenever they're in a diene, they're closer together, and in a triene, they're closer together as well. They're only one bond apart. Then you get delocalization due to overlap between p orbitals, and this produces some extra stability within the molecule lowering the enthalpy of hydrogenation. All right, guys, I hope you found that question good or helpful, useful. I'm rushing through these videos now. I'm going to try and bang out as many as I can before the exam. So moving on to the next question. Let's go. Enough waffle.
Keep moving on, keep moving on, keep moving on, keep moving on.
Okay, question 4. The nitration of benzene uses a nitrating mixture of concentrated nitric acid and concentrated sulfuric acid. Which statement is correct? A. The nitric acid acts as a base. B. The nitric acid acts as a catalyst. C. The nitric acid acts as an electrophile. Or D. The nitric acid acts as a reducing agent. So we can go through and basically explain why certain ones are the wrong answer. So if we look here, nitric acid as a catalyst, well, HNO3 it becomes NO2 plus, and therefore that NO2 plus, if you remember in the nitration of benzene, joins the benzene ring, so the catalyst cannot reform. That means that, HNO3 cannot reform because it's actually used up in the nitration of benzene. So it's not a catalyst because catalysts get reformed. The catalyst in this is the H2SO4 because it forms HSO4 minus, and when the hydrogen is substituted on the benzene ring for the NO2, that joins the SO4 minus to become sulfuric acid again. So that's the catalyst. The next one, it says HNO3 acts as an electrophile. Well, it's not the HNO3 that acts as an electrophile. It's the NO2 plus. It's that nitronium cation that forms the nitrate group on the benzene ring. So that is the electrophile, not the HNO3, although it does come from the HNO3. And then HNO3 acts as a reducing agent. Well, a reducing agent themselves get oxidized. So does it lose electrons or does it gain electrons? Well, let's check the oxidation state. What is the oxidation state of nitrogen in HNO3? It's going to be +5, the hydrogen's going to be +1 and the oxygen -6. And then when it goes to NO2 plus, the nitrogen is also going to be +5 as there's two oxygens which are going to be -4 and there's an overall +1 charge. So it hasn't actually been reduced or oxidized. So it's not acting as a reducing agent. So that leaves our final answer. It's a base.
You're still here? It's over.